Thank you everyone for being here. And I'm excited to present our work on higher order label homogeneity and spreading in graphs, which is joint with my colleagues from Georgia Tech and Carnegie Mellon. So given a graph, say a friendship network, and let's say you know that Bob and Carol like Arsenal, are fans of Arsenal, and Alice isn't, what can you say about Smith? And can you use this information to recommend Arsenal products to another person, say John? Or say in another friendship network, when you know what kinds of products people purchase, can you use that to determine what product some other person in the same network might purchase? And can you use that again for targeted ads placement? So more generally, I'm talking about the problem of semi-supervised vertex labeling, where you're given a graph of vertices and edges, such as a friendship network, and labels for a few vertices, such as Dave buys Apple and Elisa buys Android. And you also have some notion of homophily, that is neighbors, that is connected pairs of vertices in the graph tend to have the same labels. And your aim here is to find labels for all the vertices in the graph, either for recommendation or ads placement or any other application you can think of. So the motivation from our work comes from one shortcoming of many prior approaches which work by propagating information throughout the graph. So the general structure of these algorithms is as follows. So they begin with some initialization step where the label vertices begin with some known values and unlabeled vertices begin with some default or random values. And in each step of propagation, each vertex updates its value based on that of its neighbors. And this continues iteratively until convergence happens. So this is a deliberately vague description of these algorithms. For instance, what are values here and how exactly are they updated? And it turns out that the specifics of what values are and what update rule is what distinguishes one prior work from another. And specifically for us, we'll focus on prior work, which is labeled spreading. Um, Here, labels are probability vectors or plus or minus a constant offset, such as, say, 0.9, 0.1. And the update rules, so we are having all of these labels for all the nodes in the form of a label matrix, and that's going to be updated as, to some extent, it's going to come from the supervision that is provided, which is the given labels for some of these vertices, and to some extent it's going to come from the labels, the current label assignments for their neighbors. So this process is repeated iteratively, as we saw earlier, and it turns out that it can also be neatly expressed as a loss function, which has one term corresponding to supervised loss and the other constraining labels on the graph to be smooth. And it turns out that this also has a closed form solution and pretty nice convergence guarantees, which is why label spreading tends to be widely used, since it can scale well as well. But where our work really comes in is based on this observation that can be expressed really well using this small example. So let's consider Alice, who has four acquaintances shown in blue and three close friends shown in red. So here, blue represents, say, an opinion that is shared by vast majority of the people, and red is like an opinion that's shared only by Alice's close friends, as reflected in the closely knit community structure. So now the observation here is that if you rely on just edges as previous methods do, then since Alice has four blue friends compared to three red friends, you might be tempted to label her as blue. On the other hand, if you take into account the higher order structure, then you'll be able to label Alice correctly as red. So this is pretty common in real world graphs because the number of acquaintances in general, say on Facebook, is much larger than the number of close friends. And this leads to a severe underprediction of unpopular opinions, or such as red in this case. So the driving hypothesis of our work is that can cliques, higher order cliques such as triangles or 4 cliques and 5 cliques and so on, are they more homogeneous in labels compared to edges? And hence, by using cliques, can you improve the accuracy of vertex labeling tasks that you care about? And So just a short answer to both of these questions is yes, and that's what the rest of the talk is about. So I'll begin with some evidence to show that cliques are more homogeneous in labels than expected by random chance. And in fact, this homogeneity only increases as you go, as you increase the size of the clique. So we ran empirical study on 4 large data sets coming from different domains with various, with variable number of classes from 2 to around 42. And the way we study this is to come up with this notion of a label configuration. So if you take a particular edge, then either the both incident vertices can have the same label, which we call as the 2 label configuration, or they can have different labels, which we call as the 1 label configuration. And you go and count the fraction of times each of these label configuration is observed in the graph. It turns out that they're observed at 40-60 ratio. And this is significantly different from what is expected by random chance. In particular, the most homogeneous label configuration, where edges, both incident vertices have the same label, is much more common observed than expected. When expressed in terms of relative prevalence, which is the height of the orange bar here by the green bar, you can see here that when edges having same label is 2 to 6 times more common than expected by random chance. And this idea of label configuration can be generalized to higher, larger cliques as well. So for instance, for triangles, we have 3 label configurations. One where all of them have same label, another where 2 vertices have same label, one has a different label, another where all the vertices have different label, and so on. So for 4 cliques, we have 5 label configurations, and for 5 cliques, we have 7 label configurations. And we'll now see how the distribution over these label configurations look like. So note here that the labels themselves are kind of exchangeable. So as long as it is 3 label configuration, it doesn't matter whether all of them are blue or all of them are red or so on. And when you measure this, what we observe is that as we increase the size of the clique, the most homogeneous label configuration is becoming increasingly prevalent as you go from K2, which is the edge, to K5, which is 5 clique. So here, so what 2 things to note here are that one, most homogeneous label configuration is more prevalent than expected. So you can see here that the blue bar in all of these pictures is much larger than 1. And the other thing is that the ratio of the ratio of these, the proportion of these differences actually keeps increasing as the size of the clique increases. And this can also be similarly explained in terms of how rare the most inhomogeneous configuration of clique becomes as you increase the size of the clique. So this can be leveraged in an algorithmic framework, which can apply to many algorithms that fall under this category of propagation approaches. So recall that most of these algorithms work by sending messages across these across edges. So say a triangle is an important higher order structure that we want to take into account. Then we envision a framework which also passes similar messages via triangles. So, and in general, given any subset of higher order network structures, you can think of messages being propagated along these structures. And here, edge is just a simple higher order structure, and that prior methods consider, and we want to generalize it to any kind of structure that we might want to leverage for label spreading. And specifically focusing on higher order version of the label spreading algorithm, what we are able to show is that a higher order label spreading on the original graph is equivalent to label spreading on a modified version of the graph, where the edges have been reweighted based on how many higher order structures they are incident on. For example, here, if edges and triangles are your structures of interest, then the reweighting of the edges will incorporate some amount of the weight will come from the number of edges that 2 people share, and some amount of the weight for the edge will also come from the number of triangles 2 people share. So in general, the more the higher order structures that 2 people share, the stronger the connection becomes in the modified graph, and hence these pair of friends are incentivized to have the same label during the optimization procedure. So since we are able to show that label spreading, higher order label spreading is equivalent to label spreading on a modified graph, all the theoretical properties such as closed form solution and convergence guarantees for the original algorithm carries over to our higher order label spreading method. We evaluated this experimentally on all the 4 data sets that we saw earlier. And here I'm plotting to what extent the use of higher order structures helps improve accuracy compared to using just edges. So note here that this is accuracy increase percentage compared to edges. So for all of these networks, the baseline performance for edges is like accuracy increase is 0. And you can see here that across all the networks, the use of higher order structure helps. And it turns out that for most of these cases, the best performance is achieved by just including triangles. And the larger structures bring in diminishing gains. And to understand the specific examples of cases where we are able to see these improvements, we pulled some case studies from the political blogs data set. So here, question mark denotes the vertex whose label is of interest. And it turns out that the red and blue labels were the ones that were supplied by the algorithm, and the others are unlabeled vertices. And when you use just edges for labeling, you can see here that 2 hops away, many more uh, vertices are red compared to blue, and hence label spreading classifies the question mark vertex as red. On the other hand, which is actually incorrect based on ground truth. On the other hand, when you use both edges and triangles for label spreading, you are able to see that even though there are fewer blue labeled vertices 2 hops away, they are connected by a tighter triangle structure, which can be used for correctly labeling this vertex as blue. And there were other examples as well where a similar thing happened. And we also compared the algorithm to prior methods, both traditional label propagation, label spreading methods, as well as more recent representation learning or graph convolution networks based methods. And in general, what we observe is that higher order label spreading is very outperforms label spreading and label propagation just based on edges, and is highly competitive with recent methods and outperforming even recent methods on 3 out of 4 data sets. And it's comparable or faster in running time, especially it tends to be about like 10 times faster compared to more recent methods, giving comparable values of accuracy. And it tends to be as fast as the traditional methods, which rely on very fast sparse matrix operations. So to summarize this work, we started with the hypothesis that higher order structures are important, carry important information, and hence they can be leveraged. And we saw some evidence to show that they are indeed more homogeneous. And we developed an algorithmic framework to incorporate higher order structures for label spreading. And experimentally, we were able to show that usage of higher order structures helps. And we saw some examples of specific cases where it helps as well. And I'll be happy to take any questions. Thank you.
Okay, thank you for your very interesting presentation. So any question?
Hi, I have a question, and thanks a lot for the presentation. That was super interesting. I have a question regarding the how the difference in prevalence might increase. In one of the graphs, you show that for a certain structure, it increases much more than expected for the random case. And I'm wondering if there's any intuition. Yes, that's the slide. Is there any intuition in like how much does it increase? Does it perhaps depend on something like the size of the clique, like order 2, like the square of the size perhaps, since in the clique you were counting like it has the size of like n square order of magnitude. This is just my intuition, but I'm wondering what your thoughts on that are. Thank you.
Yeah. So that's a great question. And I don't have a good answer for that. So you can see here that the ranges of increase also differs significantly for the 4 networks that we studied. So I don't know if there is a concrete like proportional to k squared or some function of k that we can expect. But I think as we also increase like k to study much larger cliques, then a pattern might emerge, and that would be interesting.
All right, thank you.
Okay,
Hello,
thank you.
for your
Please speak. Yes.
hello, thank you for your presentation.
Thank
So,
you.
so I'm wondering what is the difference between label propagation and the label spreading?
Oh, so it's in the use of the graph Laplacian for yeah. So it lies in what Laplacian is being used in the loss function. So label spreading uses the normalized symmetric graph Laplacian, which is it's like symmetric normalized graph Laplacian, whereas label propagation just uses the unnormalized graph Laplacian, which is the degree matrix minus the adjacency matrix. So that's just a minor difference in the kind of regularization the graph structure is used to enforce.
Okay, thank you.
Okay, next question, please.
Hi, thank you for your presentation. I have two questions. The first one is, what is the time cost to consider a larger K in the clicks in your experiment?
Yeah. So the overhead compared to label spreading algorithm comes from the construction of the modified graph, which involves enumerating cliques. Once the cliques are enumerated, even as they are enumerated on the fly, you can compute what these modified edge weights are going to be. And the modified graph is guaranteed to be at least as sparse as the original graph. So there are a lot of recent work dealing with click counting and how to do that extremely fast. So in generally speaking, the counting time, the time to count a k click of size k increases exponentially with k, but in practice this tends to be extremely fast. So for instance, on our largest data set, which had around 22.3 million edges, we're able to count all cliques within like 20 seconds on like my laptop. So it tends to be pretty fast for data sets that you can load in memory.
Okay, thank you. And another question is, in this work, we only have one label in one node. Can this work to be extended to multiple labels for a node?
Yes. It can be extended to multiple labels per node. So I guess one way in which I can think of I guess dumb way in which I can think of doing that is to just do uh, like label spreading for each label separately, saying whether that label is present or not, and then combine all the results. But if there are like base algorithms that do semi-supervised vertex categorization instead of classification, like you said, then this algorithmic framework can be used to like apply that algorithm after constructing the modified graph as well. Does that answer your question?
Okay, thank you.
So any other question?
I have one question. Thank you for your presentation. I'm just curious. I think at some point in the experiment, you mentioned that the algorithm outperformed the baseline on 3 data sets, and there was one last data set where it didn't outperform the baseline. I would just like to know what are your thoughts on why that was the case.
So yeah, so I think where triangles help the most, so there are multiple reasons for where triangles might help and where it might not. So for example, I presented 2 case studies where triangles do help. So in general, this depends a lot on how much more homogeneous triangles are compared to edges in these networks, and also how triangles are distributed throughout the network. So for instance, even though triangles are more homogeneous, if all of them are concentrated in a small locality, then many of the vertices do not benefit from using triangles for edge vertex labeling. So that's like one high level answer for like where triangles might help and where their help might be like limited. So as for where it might hurt, whenever the hypothesis that we started off with does not hold, it might not help. So I guess we saw two cases here where like a tighter community structure indicated that even a less popular opinion is the opinion that the question mark vertex shares. So there are few examples where the opposite is also true, much fewer, but there are such examples as well. So this political blocks dataset is a small dataset, so this results from a mislabeling of one vertex compared to this baseline algorithm. So that's why this is not a statistically significant worse performance on the part of higher order label spreading. So that's also something to keep in mind.
I see. All right. Thank you.
Thank you.